Okay, so yeah, I'm very happy to welcome Manuel Endres as our speaker for today. Manuel is professor of physics at Caltech. I've had the pleasure of knowing him since he was a PhD student in the group of Emanuel Bloch. He received his PhD there in 2013 from LMU Munich, and he did amazing work building the first quantum gas microscope, using it for site-resolved imaging of the superfluid insulator transition, and more broadly studying quantum correlations and dynamics of ultra-cold atoms in optical lattices. And he received the Otto-Hahn Medal of the Max Planck Society for his excellent PhD work. He then actually did a one-year postdoc in theory in the group of Ignacio Serrat before moving on to Harvard as a Harvard Quantum Optics Enterprise postdoctoral fellow. And there he did really pioneering work on kind of bottom-up assembly of arrays of individual atoms in optical tweezers, using a technique that is becoming really widely adopted by many groups around the world. He started exploring the many-body dynamics of the system under the influence of Rydberg interactions, and he's continued to push that platform forward in his group at Caltech. So I think you'll hear today about this vibrant research program in applying these atom arrays towards quantum computing and quantum metrology. He's received numerous awards for his work, including the NSF Career Award, the LSR Young Investigator Award, and quite recently also the Breakthrough Foundation's New Horizons in Physics Prize. So we're very fortunate to have Manuel here, and we're looking forward to your talk.
Thank you for the very thank you for the nice introduction. Can you hear me? Yes. Okay. Okay, so first of all, thanks for inviting me. I already had a really nice morning discussing with various people in the audience and learning a lot of physics. And I'm looking forward to meeting more of you in person. I'm going to talk, give some kind of broad overview of different directions of doing quantum science of various types in tweezer arrays. And then we'll focus a little bit on some results from my group from the last 2 years. So let me jump right into it. This guy doesn't work anymore. You have to click somewhere. Oh, it just worked. Let's try one more time. Try it out. Just got 1 second ago. All right. Okay. So in our group and more broadly in the field, we're interested in various types of directions. For example, quantum computing. We have a leg in quantum simulation, which is to study quantum many-body systems in some sort of precise fashion. We're also increasingly interested in quantum metrology, which is to use quantum states or system for precision measurement, in particular entangled states. And lastly, maybe in the future, we want to link up these systems via quantum networks. So this is great. And in the end, the goal of these directions is to outperform classical counterparts. So you want to build a computer that's faster for certain tasks, or than a classical computer can solve a certain task which would be impossible in a classical computer. So this is great, but for most of those applications where you really, I don't know what's going on. Is it there now? I really jump again. Okay, does anyone have a pointer? There's a laser pointer potentially. Work just briefly. Sorry for that. No, this works again. Maybe I'm just too far away. Some of the laser doesn't work there. Okay. Anyway. Okay. Yeah. All right. Anyway, so we'll just work like that. I think it should work. Okay. The key ingredient for really outperforming classical counterparts in most cases is large-scale entanglement. So, and I want to walk you through why it is actually so hard to build large-scale entangled systems. I imagine you start with a bunch of 2-qubit systems in a product state, and you try to build a highly entangled state out of that via subsequent gate operations. So you go through it, say, you do 2-qubit gate, make a bell state, make more and more complicated entangled state, and at some point it becomes very complicated superposition state. So if you have local interactions or local gates, this follows some sort of a light curve to a certain degree, and that's generically true. What that means is that the time scale you need to entangle the whole system grows with system size. I give some sort of simple law, which is, in most cases, it's the linear extent of the systems. There's some exceptions like building GHZ states, it's logarithmic in the extent, but it will always grow with the system size typically. Okay. At the same time, you can have errors in the system, and you have more and more qubits as you scale up. And that means that the total error rate actually grows also with the system size, just because at a certain error rate on a single qubit rate, single qubit level, you can just catch more and more of those errors at a given time step. So if you put this together and ask yourself, okay, what's the probability of actually making a very entangled state, large scale entangled state, in a system of size n, you will get a law like this. So you put together this error rate, okay, and the time scale you need for total entanglement. So you get an n from here, and then you get something that depends on n here. It might be this form or something else. But what it boils down to is that this probability of making no error actually super exponential in system size. So it's actually more than exponentially suppressed. And this makes this so hard, and this is why you typically only see, say, GHG states or something like this, like 20 atoms, 30 atoms, or something like that. So I think that's a fundamental reason. So this has a certain implication. So it's hard, and it implies that we need very low error rates at the single and 2 qubit level, or atom level, depending on what you want to do. And eventually we'll need large system sizes to provide the necessary overhead to do quantum error correction. Because no matter how low your error rates are, like you will maybe end up with 3 nines, 4 nines, but you have these kind of laws, it actually quickly becomes very, very difficult to go to so large scale systems like thousands of qubits. Okay? And our approach to this challenge is to use neutral atoms in tweezers. And I want to walk you through this step by step now, and I hope you convince you that we have some interesting things to say about this. Okay, let me start with tweezer arrays, very basic. I think most people have heard this. Tweezers are a very tightly focused laser beam, and you load this from a magneto-optical trap or some like storage of cold atoms. And if you do this right, you will see that you have either 1 or 0 atoms per tweezer. It's a little bit stochastic, so sometimes it's there, sometimes not. But due to light assisted collisions, it's typically never more than 2, and this has been shown in the seminal paper by Philippe Granger already. We make tweezer arrays, and there's two techniques. One is spatial light modulators, and one is acousto-optical deflectors. Let me explain acousto-optical deflectors. It's quite easy. You have one incoming laser beam, and then you basically deflect the beam with an RF wave that like runs into a crystal, some sort of a photon collision. And depending on the phonon frequency, you can deflect the laser beam in different directions, basically. So now if you send in multiple RF waves, you get multiple photons and you get multiple laser beams out. And with this, you can make basically a 1D array. Now you can cross these two devices and you can get a 2D array. So here's an image of tweezer light. It's not atoms yet. I'll show you some large scale arrays towards the end. So you see, for example, with these crossed AOTs, you can easily make like 10,000 tweezers or something like that. Okay. If you load atoms into this is a small array. It looks like this. So this is a fluorescence image of an 11 by 11 array. And you see the stochastic loading. And what you do is you repeat the whole sequence, load from a magneto-optical trap, take an image, start from scratch. But you see that every time you basically have a different loading pattern. So the question is then, okay, how do you really get a defect-free atomic array to do some kind of interesting quantum size? Where in most cases, you want to have not that, but you want all of the sites fit. So the technique to do that is goes on an atom-by-atom assembly, and it's something I co-developed in my postdoc. It's quite easy in a sense. Conceptually, you load atoms from a magneto-optical trap, and you have the stochastic fitting pattern, and then you do some sort of a feedback entropy removal. Basically, you take an image here, and if you're very good at identifying the tweezers, you can just say, okay, this guy is full, this guy is empty. Let me just switch off the empty ones and rearrange all the other guys into a defect-free array. And you can do this, for example, by feedbacking onto this RF waveform that goes into this acousto-optical deflector. So it's relatively straightforward. In principle, in practice, you have to be very fast and very high fidelity in the imaging and so forth. And this is some sort of a standard technique by now. So this is in 1D. In 2D, you do something slightly different. You have some array that you make with some technique, could be an AOD or an SLM that's static, and then you use an acousto-optical deflector and really pick up atoms one by one and rearrange them. Okay, so that's some sort of the more advanced version of this. So now this is at this point, some sort of a standard technique that in many groups is used, and it has certain features, so you can make defect-free arrays at this point that are like hundreds of atoms, maybe 1,000 if you really push it. It's typically in 1D, 2D, and maybe you can go a little bit 3D. Okay, the geometries are very, very flexible, so you can put this in different types of lattices, you make all kinds of patterns. And one thing that's quite important, it's much faster than doing a traditional, say, ultra-cold atom experiment where you do evaporative cooling. And that's actually quite important in terms of data rate for this experiment. Okay, now these are neutral atoms, and then these tweezers, and they're at relatively large distances, say a few micrometers, and typically they wouldn't interact. So you have to do something special to make them interact. So and the way we do that is we excite them to high-lying Rydberg states, and in the end, there's some sort of a dipole-dipole interaction. I'll explain this in a second. You could do something similar with molecules, and this has been pioneered over the last years by for example, Caltech or like John Doyle. They do various things like that. You can do other things. You could, for example, stick them into a cavity, and I know that John and various people have tried that also. Monica has some sort of experiment. It's similar. Maybe not with single atoms. So you can basically have them as a control mechanism to place emitters into a cavity at specific distances and then have photon mediated interactions. Or if you're brave, you put them very close together and let them tunnel between the tweezers. Okay, so this is some sort of the flavor of this, and I'm not going to list all the groups. There's many, many groups that do one of these things. So let me really kind of zoom into the story with Rydberg states. So how does this work? So imagine you have a neutral atom in its electronic ground state. I'm talking about the outer electron. And the electronic waveform is typically quite small. And now what we do is we excite them to very high-lying principal quantum numbers, very large quantum numbers. So it means the wave function basically blows up to sizes that I find still kind of surprising, that you have this few hundred nanometers. And the most important consequence of this is that you have a very strong polarizability with electric fields. What also happens is that then you get very strong induced dipole-dipole interactions. So you have a fluctuating dipole moment on one side and on the other side, and you get these very, very strong van der Waals interactions between Rydberg states, and they scale dramatically with the principal quantum number. So that means you can make them extremely strong. Okay, and they have a distance scaling 1/R6. And if you plug in some numbers, so if you take some random alkali atom, you will get something like this, that at 2 micron, you can have an interaction. It's 10 gigahertz, which is gigantic for an atomic physicist. Okay. And at the same time, the lifetime of these things is pretty long. So it's 100 microseconds. It's not forever, but you have a quite good ratio of interaction strengths over lifetime. Okay. And in a sense, this is very well suited for the typical atomic distances that we have in these Tweezer arrays. And this is some sort of where this fruitful marriage actually comes from. Okay, so let me go a little bit into more detail because it will play a role in a second. So imagine you have a bunch of these atoms in a Tweezer array and you just shine in one of those, a laser. It could be 2-photon transition, single photon transition, doesn't matter. But let's say you have a ground state and a Rydberg state and you couple them with a laser. And you can map that then into a spin system and a rotating wave approximation, a rotating frame. And you can write down essentially a spin model. Okay, so without the interaction, you just have a driving term. And there's some sort of omega, the intensity controls sigma x terms, and delta, the detuning, controls the sigma c term. And then with the interaction, you get a density-density interaction that's of Ising type for the experts. And it's such that only the Rydberg states interact to lowest order. If you're in a ground state, then the interaction is very, very small, so you can neglect it. So you have these projectors onto Rydberg states, and this gives you this some sort of like longish range Ising model, because they have this 1/6 interaction. That's controlled by a transverse and a longitudinal field for the many-body experts in our audience. And our key ingredient here is that with these Tweezer arrays, we can space atoms in flexible patterns that gives us control over this interaction matrix to some sort of degree. Okay, and that's actually quite powerful. So now, this type of approach combining Tweezer arrays with Rydberg Hamiltonians, and there's many variants of this, I only showed you one, has been used widely in the last years. In some sort of 2 different directions, roughly. One is doing quantum simulation of many-body physics, and the other one goes a little bit more towards quantum computing and some sort of digital approaches. So on that side, naturally, there's a spin model. So there's quantum phase transitions. You can study quantum magnetism and so forth. You can also run these things out of equilibrium. And for example, quantum many-body stars have been observed. There's forays into topological physics, and there's a lot of different open ground in this system. I write confinement. There was just a paper today where people saw confinement of quasi-particles. On the other hand, on the quantum computing side, let me distinguish maybe 2 things. So one is just thinking about, okay, how good am I at, like, say, 2-qubit gate or like entanglement between 2 qubits? And then there's 2 versions of this. One is really in the manifold that I just showed from a ground to a Rydberg state, and there we can entangle atoms at like close to 3 nines, and I'll show you the data in a second. But more importantly for quantum computing, what you want to do is entangle states in long-lived qubits, and I will explain that in a moment. So you have long-lived qubits in a hyperfine state or an optical transition close to the ground state, and you only temporarily go to the Rydberg states to basically provide 2-qubit gates. And so the fidelities for that, some sort of at the 995-ish range, and I'll show you some sort of new data where we push this now to 997, and I'll also show you a pathway to make this like to like 3 nines fidelity in a minute. So going to larger systems and really building together like a toolbox of digital quantum computing, I'll explain in a second how this works. There's various groups using this, so people have built universal quantum computers in a few different groups. Harvard managed to do this kind of seminal work, actually really doing algorithms with logical qubits, error-corrected qubits to a certain degree. And I'll explain a little bit our work that's somewhat parallel to Adam Kaufman's work, where we really entangle actually optical transitions, where we do some sort of a hybrid of quantum computing and clocks. Okay, so that being said, our results in this context, they fall in 3 categories in a sense, or at least the recent ones. One is really doing high fidelity analog quantum simulation, and I'll walk you through this in the first part of the talk. The second is to merge quantum computing techniques with metrology, specifically with atomic clocks. And the third one is to scale tweezer arrays to much larger system sizes. So the first part for the experts, it's done with strontium atoms, with the alkaline earth atoms, and the last part is with cesium atoms, with the alkaline atoms. And if I have enough time, I'll try to go to all of this somewhat briefly. Let me jump right into it and talk about the high fidelity quantum simulation part. So this is done with strontium. Strontium is a 2-valence electron atom. It's typically used in optical clocks because it has a very narrow dipole photon transition here that you can use as an optical clock standard, basically. There's a cooling transitions and broad transitions. And in the beginning, our goal was to actually develop some sort of the toolbox to even trap these types of 2-valence electron atoms in tweezers. And we managed to do that in parallel with 2 other groups. It's Adam Kaufman and Jeff Thompson, and it's heavily inspired by a turbine quantum gas microscope. So we managed to do that. We did like first imaging and narrow line cooling, and we don't want to talk about this here. High fidelity imaging. We then managed to actually build an atomic clock out of that. I'll come back to this later. And then eventually, and this was very, very important, we figured out how to do very high fidelity Rydberg excitations in there. And I want to walk you through that part briefly because it's some sort of illustrated. So the way this works is relatively simple. You start in the absolute ground state of strontium atoms, and then you move atoms via an ultra-narrow clock pulse into this very, very long-lived metastable state here. So there's a specific thing of 2-valence electrons that exists. And this state lives extremely long compared to the timescales you need to perform, for example, analog quantum simulation in the Hamiltonian that I just showed you. So you can forget about this ground state for a second, and I'll come back to it later. So this is some sort of a very specific scheme where you can go from a P to an S state with very high Rabi frequency and relatively little decoherence. Normally, you would have to do this in some sort of a 2-photon transition from S to P to S, where you get additional decoherence from intermediate states. So this is nice. We can get very, very cold through cooling on these narrow line transitions. And there's also new detection schemes that are quite important to reduce spam errors on these analog quantum simulators. For example, we use auto-ionization via core excitations that I don't have time to talk about, but it improves the Rydberg detection fidelity dramatically compared to previous work. Okay, so let me just show you some kind of very simple results. So let's imagine you take these atoms in the tweezers and you space them very far apart so they don't interact. So this 1/6 interaction is very, very small, and you just shoot in a laser beam on resonance with that transition. So delta would be 0. And you see just very simple Rabi oscillations. So you see this textbook Rabi oscillations with very high contrast. You can see 50, 60 oscillations. So this was very important when we saw it first, and was the first coherent Rydberg control of single alkaline earth atoms. And at the time, also with record fidelities generally across the field. And this is now a scheme that's very widely used to go from this metastable state upwards. What about entanglement? It's relatively simple. You use so-called Rydberg blockade. So what you do experimentally, you put atoms into pairs that are very closely spaced. So within the pair, you have a very close spacing, and you put the pairs far away so they don't interact. So within a pair, the level diagram is simple. So you have Chi, ground Rydberg, Rydberg ground, or Rydberg Rydberg. So if you're far away, this is just what I showed you. You have basically no interaction. You see this kind of regular Rabi oscillation. So now if you're close by, and this Rydberg interaction can become extremely strong, as I mentioned. So typically, these Rabi frequencies are maybe 5, 10 megahertz if you push it. And this Rydberg interaction can be ginormous if you want. So you try to make this Rydberg interaction much larger than a Rabi frequency. And if you do that, this double excitation becomes essentially off-resonant and forbidden. That's the so-called Rydberg blockade. So now what happens if you look into the details of the Hamiltonian, you don't excite one of those states, but you actually excite a superposition state to the symmetries in the Hamiltonian. And the superposition state you should reach with a square root of 2 enhanced Rabi frequency. And this is what we see in experiment. That we see, for example, here the time is like whatever 70, and here is down to 50. And there's exactly a square root of 2 in this kind of enhancement. And importantly, this state here is an actual a maximally entangled belt state, GR plus RG with some phase. And you can characterize then the fidelity to go to this belt state. Essentially, you start here and do a pi pulse. You go from here to here, and you have to then characterize the fidelity. And we did this back in the day in 2020. And then if you correct for state preparation measurement errors, you can reach the state like with a fidelity of 9.9, meaning you have like about a 1% error rate of doing that. So now in 2023, we repeated that, and with some tricks and improving all of the error budgets, we managed to get to very close to 3.9. So we do this like a 0.1% typical error rate. So we're very, very good at controlling this root-back transitions from these metastates. So now let me briefly talk about the many-body side of things. So I showed you this slide, and we worked very, very long. Adam was in the audience who led this heroic effort that took a long time to actually probe this type of physics. So we wanted to probe some sort of how good are we in actually generating very large-scale entanglement in these arrays. So let me just be a little bit more specific. So we start with these root-back atoms in an unentangled product state, and essentially just quench it with the Hamiltonian that I just showed. And we tune the system parameters such that we are in a chaotic regime, and we are there's a many-body workshop. We are at effective infinite temperature. Okay, and what happens then in this regime is that you build entanglement entropy, that's the entanglement between two halves of the chain, in a linear fashion. So this entanglement entropy grows linearly and then saturates to a certain value that depends on the system size. So there's two features in here. One is the saturation value depends on the system size in a linear fashion. That means in 1D you're in a so-called volume yaw state that you are at long times. And the other feature is that the time scale you need to actually go to this volume law state grows also with system size, and that's a direct manifestation of this light cone physics I just showed. Okay, so why are we interested in that? So like we're interested in basically trying to understand how good our quantum simulator is in producing these volume law entangled states. And there's some sort of many motivations for this. One is it's very hard to capture in classical algorithms. So once this entanglement entropy is too large, it will be tricky to actually represent the state, because you're going to truly need number of coefficients that grow exponentially with the system size. That's not always true. People always say this is true for quantum mechanics, but you actually need a complicated entangled state for this. Okay, so that's one test case. And on the other hand, it's also a native benchmark just for how good our quantum simulator is in non-equilibrium dynamics. Okay, so here are some results. You can look at, for example, the fidelity as a function of time. There's a weird unit, forget about it. So this is some sort of effective time. And you see the fidelity of reaching as a function of time just drops. Okay, so you have a certain error rate. And the error rate increases with system size. You see, for example, this dashed line becomes steeper and steeper as you go larger. And nominally, you would expect an exponential decay if you have very simple noise sources. In our case, there's some deviations here, and they're quite interesting. They come from the fact that a lot of the noise sources in these systems are highly non-Markovian. So there's very strong temporal correlations, and then there's, in addition, also spatial correlations. So there's a deviation from strict exponential decay. Okay, so then what we did is like you run each of those system sizes to whatever time scale you need to actually build this volume law. So for larger systems, you have to go a little bit longer. And then you can record the fidelity, meaning how good are you in producing those states without an error as a function of system size. And this is some sort of the final plot here. So you see system size and the fidelity when you reach this volume law state. And you see this drops in a super exponential fashion. In fact, this line here is actually this law that I just gave you with some coefficient in here. It's exactly that line. And you see it follows that line very, very nicely onto a certain system size. And at some point it deviates from that. It comes from these non-Markovian noise sources. So just to give you a bit of a sense of the scale here, so we actually managed to do this, to produce this volume law entangled states for 60 atoms with about a 10% fidelity. So 10% of the time we make no error. And this is actually very, very high if you compare this, say, to these early Google supremacy claims. At the time, they had about 0.3% error rate in a 53 qubit system. It's 2D is a little different, it's analog versus digital and so forth, but it gives you a sense for how good these systems actually are. Now, these error rates in the Google experiments are also a little bit higher, so there's some sort of in a similar vein actually at this point. Okay. You can ask them, okay, did we actually achieve quantum supremacy in there? Because we have these very high fidelities, and I told you it's very, very like difficult to simulate. Okay. So we tried to actually simulate those systems up to this 60 atom system size, and then at these large-scale systems, starting from like 40 qubits or so on, there's no exact algorithms anymore. So it becomes very, very hard to do this in ED for the experts. Just you run out of memory. So you have to do an approximate algorithm, and the most straightforward one would be to do a matrix product stored algorithm. But this approximate algorithm, they also have a limited fidelity in a sense. So they also make errors because you make approximations. And then what you try to do is you say, okay, what is actually better at producing these states, my approximate classical algorithm or my experiment? Okay, and then it turned out all the algorithms we could find and tried out, they all failed. So we really didn't have any chance to go to these high fidelities at 60 qubits. And then in this collaboration that we had with Sunwon pointed out an idea from Sherman, who was in the audience. This is a so-called trick to improve throttlization, and we implemented on a matrix product state algorithm. And with this novel algorithm that we believe is the best algorithms for this type of dynamics in 1D now, we are able to beat the experiment, but it takes a very long time. So we actually never even ran it on a Caltech cluster because it's just like it's too expensive in a sense. Okay? So it takes a very long time, and we count this in core days. You can speed it up if you have multiple cores, but it gives you a sense it's not something you would just put on your laptop. Like you have to actually use the Caltech cluster, and I think Adam turns out was the largest user of the Caltech cluster for many months actually, and as an experimental group. So that's just something. So there's some sort of difficulty. In a sense, this is on the edge of quantum advantage. So it's not quite quantum advantage. In fact, if you tried the same experiment with the same fidelities in 2D, which we are some sort of will do probably one day, you would actually beat these classical algorithms for sure. So that's some sort of an attempt on that. Okay. So let me move forward. This is one paper out of a long list of papers that we wrote together with Sunwon. Let me just flash them. So there's quite a few of those. If you're interested in some sort of the gist of it, actually, I'm trying to advertise this last one that will come out in PRX that has some sort of a lot of the theory foundation. I'm not going to walk you through all of this. I just want to give you a very high-level overview of this whole story. So it took me a long time to make this slide, like a year ago or so, and I hope it's somewhat convincing. So it starts all with this idea that ergodic systems, they form a form of higher order thermalization. It goes under the name of Hilbert space ergodicity or thermalization. But maybe the easiest part to understand is the so-called Hilbert space ergodicity. What I mean is that if you have an ergodic quantum antibody system and you drive it with a time constant Hamiltonian, there's a certain available Hilbert space that's given by conservation laws that you have. So you have energy conservation or certain symmetry. So you cannot go everywhere because like you have energy conservation, for example. But within the available Hilbert space, the state, the quantum state itself actually covers that Hilbert space completely and homogeneously if you go long enough as a function of time. So you just like think about like a classical billiard, you would normally look at the phase space of that thing. The phase space is covered homogeneously. Here I'm talking about the Hilbert space. That's very, very high dimensional. It's covered homogeneously. And you can formalize that and connect this to certain concepts from quantum information theory, such as Haar-random designs, for example. So you can actually formalize some sort of a higher order thermalization, and that goes beyond like what people typically consider. And there's a version globally as a function of time, and there's a local version. So now, because this happens, there's certain observable consequences, and in particular, ergodic systems are highly universal in terms of their fluctuation. So let me just briefly explain this. Say you have some observable, like the probability to find a certain bit string, a certain like outcome in your quantum simulator, and you check the probability for that bit string as a function of time. You see kind of very strange quick fluctuations, and you have this for all different bit strings, and you can then even for one bit string just check this and make a histogram out of it. You check, for example, okay, what's my probability to be in that bin, in that bin, in that bin, and you make a histogram like that. And it turns out if you do this right, you have to be a little careful because there's energy conservation. But if you do this right, this forms a so-called Porter-Thomas distribution. So there's an exponential distribution. And this distribution is there for all ergodic systems in a specific sense. For the experts in the audience, you have to fulfill a no resonance condition in the spectrum. Okay? And this is fulfilled, for example, say by a mixed field Ising model, but even by interacting integrable systems such as the XXC model. So they all follow the same kind of distribution function, meaning the fluctuations of projective observables for the specialist have a universal form at very, very late time, the temporal fluctuations. So that's that. So temporal fluctuations are universal. I don't have time to talk about like even fluctuations at fixed time are universal in various different senses. And maybe the most fundamental thing, just talking to Sumon about this yesterday, might be that these systems, they are maximally good at hiding information. So if you look at, for example, the mutual information between two halves of the system. So I give you the bit strings on one half and you try to guess something on the other half. These correlations, they're actually minimized. They go to a fundamental minimum, and in the end, that is actually always the Euler constant. So this is some sort of, I think, in the end, maybe the most fundamental property of ergodic systems is that they're very, very good at hiding information. Okay. Anyway, so this is all fundamental stuff. So this is all great. So we see the fluctuations. We have a lot of papers on this. On a practical level, the fact that you have these fluctuations, it actually enables this efficient fidelity estimation. I didn't even tell you how I measure fidelity in a 60-qubit system. It's generically very, very difficult. But it turns out in these systems, it's not that difficult. So there's efficient estimators that you can use that are somewhat borrowed from random circuits. This is a variant or some sort of a generalization, I would say, of linear cross entropy that Google also uses. Using this, we did this large-scale entanglement experiment and actually quantified that. So that's one thing. Another thing we did that's quite important for these experiments, we actually verified which Hamiltonian we have. Normally you do quantum simulation and you're maybe not 100% sure what you're actually doing, but we actually have a very, very precise fashion using these fidelity estimators to measure what Hamiltonian we have in experiment. It's absolute key for this stuff to work. Another thing you can do if you combine some sort of the knowledge of this and the fidelity estimation, you can actually learn what kind of noise sources you have. I don't want to go into details here. So there's some sort of relatively straightforward approach to distinguish different type of noise just by looking at the output probability distribution function. So this, for the Thomas distributions you have when you have no errors, but once you have errors, actually they start to somehow concentrate a little bit. So you get these kind of peak distributions, and then depending on the shape of this, you actually know what errors you have. All right. You can do even more. You can cook up estimators for mixed state entanglement. So what I talked about so far is the fidelity to reach an entangled pure state. But you can say, okay, my experiment has errors anyway. Why don't you talk about mixed state entanglement? Because it's a mixed state. And in fact, you can actually cook up a very, very good estimator at these types of systems. And this estimator then also enables you to provide some sort of a quality factor for these experiments that people have been doing, where you can say, okay, as a function of system size, I reach a certain amount of mixed state entanglement. I think it combines fidelity and the target entanglement in a meaningful fashion. This was also picked up by Google recently, and they put all of these kind of random circuit experiments, for example, on one plot in our experiment as well. So this is some sort of actually a meaningful quantity. You see, for example, these ones that have very high mixed state entanglement. These are the ones that you might even believe that they have one-on-one advantage. I think it's very strongly correlated to the computational complexity of the classical solution. Okay. You see some unusual thermalization. I don't have time to talk about this. In a summary, like what we did with Sumon is like we looked at ergodic dynamics and we investigate higher order thermalization. That's something that goes beyond standard quantum thermalization. And this leads to universal fluctuations. And the fact that you have this universal fluctuation enables efficient benchmarking of various types of things, such as measuring fidelity. Okay. So with this, I want to wrap up this part on quantum simulation. And maybe I'll take a quick break. So I'm going quite fast if there are questions. Either hungry or asleep. Okay, no questions. Oh, yeah. Right.
Non-Markovian.
Yeah.
And so why do you think it's non-Markovian instead of two types of Markovian, and the later ones probably collectively basic or something like that? So it kicks in.
Yeah, but there's a very strong noise mechanism that plays a role for these experiments that we know of, and that is shot-to-shot fluctuations of the intensity of that laser that you use to go from the ground to the Rydberg stick. And shot-to-shot fluctuations are very non-Markovian, actually. They have very strong temporal correlation. And that's indeed the dominant mechanism. And you could even calculate, if you're really hardcore, like Daniel Mark, you can actually predict even the fidelity decay under such mechanism in ergodic dynamics, which is a difficult calculation. But we know this is there. So we know that the most dominant noise source is non. We just didn't know that it leads to a non-exponential decay, as we did. Yeah.
That's non-Markovian noise coming from the emotional mode of like the atoms.
No. could, but it doesn't. In this case, it plays a role, but it's very small. Actually, it's not true. Adam might correct me. It's like actually potentially true. It's that this one is also shot to shot. That's also, yeah. It does also non-Markovian, but I think the dominant noise is actually intensity noise. Yeah. Okay, good. All right, let's do clocks and computers. Okay, so so this was the first part. Now comes the second part. Quantum computing meets metrology. So I told you that we're using these strontium arrays, and then there's this ultra narrow clock transition that is used in the most precise optical clocks these days. Okay, and in fact, in 2019, some sort of similar timescale as Adam at the time, we managed to build an optical clock out of this system. So what is an optical clock? It's basically you have a laser, and you try to stabilize this laser to an atomic transition, and you just read out if some sort of an error signal that you see here, and you use this error signal to feed back to the laser frequency. You basically do a long-term frequency stabilization of a laser that's already quite stable. So what you see here is a result from that paper that I still find quite interesting in the sense that this is a Hertz level resolved error signal for 80 individual atoms. And Hertz level matters because this transition is hundreds of terahertz, like so sort of the energy difference is hundreds of terahertz. So it's an extremely precise measurement, actually. So this is sort of a combination of doing a precision measurement with programmable control in the sense that, I can move the atoms around and I see individual signals, okay? And this is quite unusual, actually. This is something that's, I think, somewhat new in the last maybe 10 years in the field, that we're able to do that. Maybe in ion traps, they could do it, but not at the same kind of scale. And this is only the starting point. So what I showed you so far is, okay, we have this quantum simulation story where we go from this metastable state to the Rydberg state. Then this Tweezer clock I just showed you is this optical transition down here. And what we want to do is then combine these things together, for example, to introduce entanglement via going to Rydberg states on this clock transition, for example, to try to improve an atomic clock. We want to go even further. What we want to do is really merge an optical clock, which is this Tweezer clock, with a universal clock. So we really want to show universal circuits to build whatever entangled state we want. And we'll show you in a second why this matters. So the question is, can we merge clocks and sensors more generally with universal quantum processors? There's a question. And if so, what is this good? Okay, so let me jump into this. The results. So we managed to do this over the last year. So we managed to do arbitrary single qubit rotations. We managed to do 2-qubit gates and circuits. And the way we do circuits is some sort of borrowed by this from this famous Blufstein paper. So we move atoms around to get arbitrary connectivity. For example, we can make gates locally here, 2-qubit gates. It's all to do with this kind of pairwise blockade. And with this, you can really program basically an arbitrary circuit in a sense. It's really universal. And then you can maybe do some sensing operation. And we managed to mid-circuit readout in the end. This mid-circuit readout, I don't have enough time to do it, but just for the people who are interested in that. So we do this via shelving information in motional states, since I talked to someone about this morning. So what we actually do is we take information on this optical transition, so superposition states, and we move them in motional superposition states. And these motional superposition states, they're in an excited state, such that they're shelved from imaging light. So you can do local readouts. So by this, you can actually read out certain atoms and then put back the information for the other atoms that you didn't read out. So this is a way to do mid-circuit readout, and remarkably, these motional superposition states, they actually live for like hundreds of milliseconds, which is actually not so obvious, but maybe it is obvious because they don't couple to it. It's motional states, so they don't couple to electric fields or magnetic fields. Anyway, so this being aside, I won't have time to talk about this, but I want to talk briefly about how we did this kind of universal programmability and some sort of what type of fidelities and so on we reached there. So let me jump into the single qubit rotation. And for every AMO physicist, that's a slide I hope they can understand, but it's still kind of cute. So the idea here is the following. So we utilize the local phase relationship between atom and light. So this is an optical transition. So it's not microwave, so it's optical. So the wavelength of this laser is relatively short. It's like a 698 nanometer transition. So, and what we do is to address atoms, we don't use addressing beams. We just move them around with lasers, with the tweezers themselves. So let's do a Ramsey experiment for the atomic physicists. So you take two atoms, okay, and you put them into a superposition state, pi/2 pulse, and then there's a local relationship between the laser phase that you have and some sort of the position. So, and let's say the atom that you don't move, you do a pi/2 pulse and another pi/2 pulse, and then the atom ends in the up state. It's relatively clear. All right. But the atom that I move, I do a pi/2 pulse and then I move it, I actually get a phase shift. I get a phase shift because I see a different phase of the laser locally. And then if you move that atom by half a wavelength, like your Bloch vector basically turns around by 180 degrees. And then if you do another pi/2 pulse, it would end downwards. So like I created like a state like this, and I did nothing else but pi/2 pulse, move pi/2 pulse. And it's a little maybe surprising at first, but it's not so surprising when you think about some sort of atomic physics carefully. So what we're doing is nothing else than a locally controlled Ramsey experiment. And with this, you can do basically arbitrary rotations. But this is a nice plot. So what we do is we do the same experiment here now as a function of shift distance. So some atoms, they don't shift, they all end up. And then you see if you shift far enough, you end down. And what you see is that the shift distance is very nicely some sort of correlated with your lambda of the laser. So this is actually the laser excitation frequency. And in fact, this is what we call a laser ruler. Actually, when we measure distances of atoms now in Tweezer arrays, we use this type of techniques because it's by far the most precise thing. Okay. And with this, we can, via some tricks, generate arbitrary local operations. Quite unusual, but it works extremely well. There's no tracing beams, very stable. Okay, let me talk about 2-qubit entangling gates. So the way you do Rydberg entangling gates, I just want to walk you through it if you've never seen this. So the original proposal from these guys down here is this. You have two lasers that you can address single atoms with, and you have two low-lying states. It could be this optical states or hyperfine states, and then you do this pulse sequence, a pi/2, and then another pi. Okay, so if you think about some sort of what happens is, okay, both atoms are down here, nothing happens, you fall off resonant. If one atom is in an excited state, okay, you get a 2-pi rotation, you get a phase shift because you go once around the Bloch sphere. If the other atom is up, you get a phase shift because you go once around the Bloch sphere. Now here's the key. When both atoms are up here, you do a pi excitation here. All right, and then this 2-pi excitation here is very far off resonant because of this very strong Rydberg blockade. Okay, that means you do not get that -1 that you would normally get. Okay? And then you go back down here, you get a -1. So there's a -1 down here instead of a +1. If atoms are non-interacting, it would be -1, -1, it would be +1. And this would be the unitary of non-interacting atoms. And it turns out, okay, you can do another small unitary, but it's basically a controlled C gate, or phase gate that you get out of this. Okay, so this has been like out there and people have done it. There's modern versions of this. There's famous Levin-Pichler gate, which was the breakthrough. There's a version of this where you can do all of this without single site addressing. And then there's a so-called time optimal gate, which does exactly the same operation, but much simpler. You have one laser beam that addresses both atoms, and it just switches on and off and just does a phase modulation. So if you time this right, you get exactly the same unitary, it turns out. And this took many years for people to sort of figure this out. But this is the one that everyone's using nowadays because it's very simple to program and it's also very, very robust. Okay. Good, so that's also what we are doing. And then the question is, okay, how do we benchmark the control C fidelities then experimentally? We want to extract the control C fidelity itself because we want to understand all the error budget from this Rydberg excitation. There's spontaneous emission, motion, intensity, noise, and all of that stuff. And it's this, and we want a sequence that's such that it's independent of preparation and readout errors, the fidelity we get. We want it to be independent of single qubit errors. That's quite important for us. These optical transitions are hard to control. So we have like close to 3 nines, that's high, but if you square close to 3 nines, you're already at 99.8 or 99.6 or something like that. So this matters. So we need something that's independent of single qubit errors and then independent of the initial state chosen, so we actually characterize the unitary itself. So to this side, we do some form of randomized benchmarking, whether or not you want to call it randomized benchmarking or not, up to you, but it works. So what we're doing is this sequence, that actually one of my students came up with. So we do an initialization block. So there's a unitary here. And that unitary already includes a 2-qubit gate. So what it does is in the 2-qubit Hilbert space, it initializes some sort of a random state. It's not exactly a random state, it's a symmetric stabilizer state, but it's a form of a random state. It's essentially a 2 design of that 2-qubit state. And then we follow this with a sequence of random single qubit rotation, control C gates, this is this guy, and some sort of compensation pulses. And this is some sort of the actual like circuit that we run. And then there's a compensation circuit here that's such that the number of single qubit operations is always held constant. And then there's a recovery unitary that if you did not make an error, puts you back into the same states. Okay? And now what you measure is, you measure the probability to come back to the initial states as a function of the number of applied C gates, as number of n. So you just make more and more C gates. Okay. And it turns out that then the slope of this, if you analyze this very carefully, the slope of this is a very good measure for the control C fidelity. We show this like very carefully in this paper down here. Right? So what we get now, if we evaluate that slope very carefully, we get a control C fidelity of around 997, which to my knowledge is the current record for neutral atoms actually. So it's the highest 2-qubit fidelity achieved with neutral atoms on these long-lived cells. Okay. So this is quite good. And then you can ask, okay, this is great, but like maybe you want even higher fidelities. What are you actually limited by? And it comes back to noise model, which is very important in practice. So we can actually model these systems via some sort of ab initio, some sort of a quantum Monte Carlo technique. And it turns out like we can measure all of these noise sources separately and actually predict the infidelity with an error bar down to this level. And we are limited essentially by spontaneous emission or emission from the Rydberg state. So they have a finite lifetime, as I mentioned, and by laser frequency. Okay, so the finite lifetime is some sort of fundamental, okay, given by the atom. But you can overcome this, and you see some sort of a trend here already. So this is the fidelity as a function of how fast you do the gate. So if you do faster and faster, you can overcome, for example, the decay noise, and this is some sort of the fastest we have achieved, and this is this 997. But you could see that if you do faster, you would overcome that. But it actually also suppresses frequency noise. What I'm saying is that we understand the errors well enough such that we can predict that with some simple technical upgrades, we actually should reach 3 nines or higher. And this is some sort of, I believe, close to the limit you can get if you don't play any kind of crazy tricks, okay? But there's a very, very clear pathway towards 2-qubit gates with these neutral atoms that are about 3 nines fidelity. Okay. All right, so let me come back to this story. So like, okay, so we did single qubit rotations, 2-qubit gates, built this circuit. So in a sense, I answered that question already. So I can merge a sensor with a universal computer. We do all of this on this optical transition, and we can, in principle, run circuits and prepare entangled states and all of that stuff. So the question is, okay, we can do that, but what is it good for? Okay, so, and I want to quickly, how much time do I have? I'm probably over. Okay, how much time do I have? We started at 12:15 we started with. Okay, all right. Fucking down, you know. All right, so let me kind of quickly go through that. Maybe there's a few metrology people I know at Stanford here that might be interested. Okay, so the first thing you might want to think about is the clock performance itself. That has various metrics. The most important one, apart from accuracy, is clock stability. It's basically the precision of the clock. So how can I improve that with entangled state? Okay, so there's a formula that's maybe a little different than people normally think about it. If you think about the clock stability, say Allen deviation, it's proportional to various factors, but like the most important one for discussion now are these two. So one is the allowable interrogation time. So typically you do a Ramsey or something like this, and if you can run the Ramsey longer, the stability would improve with 1 over the Ramsey time. But you cannot make this infinitely long because typically you're either limited by the clock laser noise that you have or atomic coherence time. To my knowledge, all optical clocks are actually limited. The good ones are all limited by laser noise. Okay, so there's a certain limit to that. And the other one is the precision of phase estimation at fixed time. That's what I call delta phi. So now, if you have unentangled states, this delta phi scales as 1 over square root of atom number. And if you have certain the right entangled states, this delta phi would scale as 1 over atom number, so-called Heisenberg. So you could get an advantage with entangled states. For example, if you have a GHG state, the phase evolution is some sort of enhanced by a factor of n. Okay, this is great, but there's a but, and the but is that there's also a trade-off, and the trade-off is that for typical entangled states like GHG states, it's also true for squeeze states if you don't play tricks. This improved delta phi comes with a reduced T, meaning you cannot run your Ramsey interferometer as long as you could do with a classical state. So you improve delta phi, but you reduce T, and typically there's no net gain. You might even lose. So let me explain that briefly, because people are always confused about it. I was so confused about it when I started, and I wish someone had that slide. So then we can explain that story. So why is that the case? So imagine you do a Ramsey interferometer, do pi over 2 pulse, and this is your clock laser phase, or the phase of some local oscillator. Okay? And then you do another pi over 2 pulse and you close it. And then what you're trying to do is you do some sort of a phase estimation. What you're trying to figure out is like, what is this clock laser phase at the end of the interferometer? Okay. And the only thing you know is the measurement at the end of your Ramsey interferometer. So it tells you, okay, I measured 0.8 atomic population. Okay, so what you're trying to do is then I say, okay, I have this 0.8 atomic population. Okay, I go on this kind of Ramsey fringe and I say, okay, the phase probably was this big. That's what you're trying to do. But now, however, if your phase, some sort of, you wait too long and the phase like drifts out of this range where you can unambiguously invert this, you might be fooled, right? Because you could say, it might be that, but it could also have been that first. So there's a certain range where you can actually invert the signal. It's a dynamic range of that sensor, basically. And this dynamic range sets the allowable interrogation time together with how good your clock laser is, basically. So how quickly this phase distribution. So now, that means you cannot run it arbitrarily long. That's true already for classical states. Now, if you have an entangled state, like a GHG state, this signal gets some sort of amplified in a sense that it's faster. So your phase response is faster with n. So now if you imagine, so you have a 2-qubit entangled state, so n is equals 2, this whole thing compresses by a factor of 2. This is not the best slide, but I did on the flight at some point. So compresses by a factor of 2. That's great. This is your delta phi, is the slope of that thing. That's the delta phi. But the dynamic range is also a factor of 2 smaller. That means that you cannot wait that long. So you have to actually stop the interferometer earlier and you have to make that time shorter. Okay? And that you lose again. So typically then you're kind of back to square one. Okay. So the dynamic range and the allowable interrogation time decreases with n for typical entangled states that are considered in this kind of scenario. Okay. So now what's the way out? So the way out of this is so-called multi-ensemble clocks. So the multi-ensemble clocks is an idea that I find very fascinating. It also still confuses me a little bit, but it's based to a certain degree on this paper that never made it into a journal. I don't know why. And very old idea of even quartz oscillator clocks. But the idea is very simple. So you have multiple ensembles that all experience the same phase of an local oscillator, but some of the ensembles are basically slowed down. So you see theta phi and they're slowed down by 2 to the k, which k is some sort of label for the ensembles. Okay. And we actually showed something like that in this paper where Adam is the first author here for classical clocks. So this is some sort of the idea. So a standard ensemble, if you don't do anything special, would see some kind of phase theta and has this kind of response, and then you can, by dynamical decoupling, this is how we do it here. Another ensemble would only see theta over 2 and this only theta over 4. So this basically slowed down. So why is this good for you? It's good for you because now I can run an interferometer very long in a sense that I can use the slow ensemble that has a very large dynamic range, it looks like, right? To basically infer the phase and say, okay, it's maybe on the left or right half. And then I can see, okay, here I'm on the right half, I'm still within the dynamic range, it's like a left or right half. And then I can very narrow it down with all of these ensembles. And then the very last ensemble I use that has the normal evolution time to do the actual phase estimation. So I get the precision of the one that runs fast and I get the dynamic range of the one that runs slow. And it turns out if you plug in all the numbers and the scaling, it actually gives you an improvement for clock, even if you just do this classically, no entanglement. Just like do a bunch of these classical ensembles and if you do this right, if you're limited by phase noise, that will actually improve your clock precision dramatically because you can improve the allowable interrogation time. So that's sort of the logic of the story. And this has been shown in a paper for us and also in a very nice paper by Shimon Kolkowitz, and also Ludlow proof is working. So that's some kind of interesting. Okay, so this is the classical part. Is there a quantum version? Yes, the quantum version is known for a long time. This is you make, for example, groups of GHG states with increasing size. So here I slow down things arbitrarily, but if you have different size of GHG states, they automatically have a different phase response that is faster and faster the larger your GHG state is. You automatically get that story if you have multiple sized GHG states, and there's some sort of illustrated here. There's a GHG states with different sizes of qubits, and this has been worked out in a number of papers actually. Even the first some sort of famous quantum metrology paper here by Giovanni and Lloyd actually spell this out in one paragraph essentially. So this has been known, and the trick is that with these multi-ensemble ideas, you can basically get some sort of the large dynamic range of even unentangled atoms together with this improved phase estimation precision of the highly entangled atoms, if you kind of play the whole game right. This is our own version of this. Actually, we try to explain a lot of these schemes in here. And this paper here actually has, I think, to my knowledge, the scheme with the best performance. It's actually truly Heisenberg for all phase priors, if you're curious about it. So experimentally, the problem with that is that it's quite complex. So what I need to do is I need to prepare different size GHG states in parallel. So they all need to run in the same interferometer at the same time. So you need a circuit that can do all of that. And this was one of the motivations why we wanted to really have a universal computer. So we actually did that then and prepared, for example, different size GHG states on this machine. some sort of a mini version where we go to GG state 4, but it's a proof of principle, and we use basically this dynamical circuit reconfigurability to actually run this circuit in parallel. So it's a GG state, 1 qubit, 2 qubit, 4 qubit, and here's some sort of the parity oscillation where again you see this kind of Mullian sample character. They all see the same phase. Okay. So now this is great. We're a little bit limited in terms of preparation fidelity of these GG states, and it's not the root back here. So here is actually how good are we with all the kind of single qubit operations on the clock. So this clock transition is hard to control, and ideally you have a very, very good clock laser. Our clock laser is only good, not very good. So we want a very better clock laser. But if we had a better clock laser, that's some sort of not even state of the art, but like somewhat closer to state of the art, and you run some sort of the estimates, you could actually in this system prepare GG states that are maybe 50 qubits, 100 qubits large. So that's not a pipe dream. I think that's actually very well possible. To actually use this then to really improve a clock that does an absolute time measurement using this Mullian sample GG states. I think it's very much possible. In particular, you can really go to Heisenberg limit at long interrogation times. I should say there's a parallel paper from Adam Kaufman where they play similar tricks, but even in that paper, they also haven't achieved that some sort of ultimate goal yet to actually kind of improve a clock like compared to the classical best clock that you could run at this kind of very long interrogation times. Okay, good. So just to zoom out. So what we're trying to talk about here is some sort of like a bigger pictures. We're trying to combine some sort of clocks with processors. Okay, and I think there's two aspects of this that I point. So one is what I just showed you. You can prepare entangled state on a clock or like on a sensor, and they might help you with a sensing task. And you could do this in addition with low dead time, specifically for this thing here. I haven't really talked about it much, but you could combine, for example, strontium atoms with rubidium atoms. What you could imagine is, oh, you do entanglement generation, swap it onto the clock. You do so your clock so sort of measurement here of the phase, and then you swap it back to rubidium, rule it out, and so on. But you could do all of this in parallel while the clock runs. You could do basically that with zero dead time at the same time. So this is sort of a scheme where we think of like separating the processor from the clock. Okay, so what I showed you previously is more like it's one thing. The clock and the processor is like one entity. It might be better longer term to actually separate. So one goal of this some sort of combination would be prepare entangled states that are useful. The other thing, which is maybe equally fascinating, is you can do coherent readout of signals. So say, I have some superposition state here. Normally what you do is you measure, send him some light, and you read out a classical signal, and you take the classical signal and you do something. If I have that combination, I could run a circuit. I have this some sort of my sensor atoms, and I can run a full circuit to process the signal quantum mechanics. And this might have certain advantages in certain cases, and there's, I think, some cool ideas in this direction. We did a proof of principle here. It's not particularly useful, but it illustrates the point. So we make, for example, a 2-qubit Bell state, and then you can read out the 2-qubit Bell state with a single atom that's an ancilla. So you do a so-called weight 2 ancilla measurement. You measure basically stabilizers here, and you read out the stabilizer. So this gives you basically the parity contrast with a third atom, but I never have to read out the actual atoms of the sensor. It is a coherent processing of that signal. So this is some sort of a proof of principle of this. So what generally I find this very intriguing in a way, because I am a physicist and we do all quantum computing and companies and so on. If you let the companies run, what they will do is they will optimize power grids, or they will factor numbers or so. I don't care. I don't care about factorizing numbers. I care about measurements, and I care about many-body physics. And I think we should really think carefully about what quantum computers are useful for measurements. So with this, let me kind of very briefly just show large arrays. I'll just flash it. It's very easy. Okay, so you can, okay, how large can you make this system? Okay, and so we have a new experiment where we try to push this really hard. So we make arrays with 12,000 Tweezer sites now. We trap around 6,000 atoms, and we do this with very large field of view objectives with lots of powers. It's just some sort of like a carefully engineered brute force approach. Let me put it like that. And you get these very nice pictures. It's again stochastic filling, and I like the kind of artsy in a way. Importantly, it is very clean. So, for example, the imaging fidelity is extremely high, like 4 nines or something. And the imaging survival is very high, with very long limited lifetime and all of that stuff. So, this is a great starting point in the sense that that system is very clean for loading, imaging, and trapping. Okay, that's good. But you want to do quantum computing, so you need to be good in coherence time, and we measured, coherence time in the system using microwave transition. So this is now not an optical transition, but a microwave one. And we see about like 12, 13 seconds of T2 time, which I think is a record for any tweezer array, not even that large. And for example, the single qubit globally controlled RB measured fidelity is around close to 4/9 as well. So this is very, very promising starting point. Some sort of, if you go like to like a silicon factory or something like the nano fab, and you see a new wafer, that wafer is extremely clean. You're very happy. So maybe I can build a computer out of this. That's the starting point where we are here. So if we want to build a computer out of this with like 5,000, 10,000 qubits, maybe 20,000, and want to do error correction with this, and some sort of, this is what we want to do. So we want to do a zone-based computer where you have a storage zone, some zone for like Rydberg interactions, some sort of a readout zone. And with this, you actually have to transport the atoms, and we have some unpublished data on that. So far, people have only transported like 200 micrometers, but now this thing is pretty large. They actually need to move atoms around really far. And we actually recently managed to transport over 500 micrometers that actually is coherence preserving. So you can pick up an atom here, put it in a superposition state, move it up here, and move it back, and basically you see almost no difference in terms of like a Ramsey, basically. We're characterizing this kind of stuff more carefully now, but it's very promising, and we think we can actually do that. I think we can actually build a universal quantum computer that is like 5,000 to 10,000 qubits, basically, with very high fidelity. I think we have all the pieces. We just have to do it and don't make any stupid mistakes, basically. Anyway, let me wrap up with that. So sort of this is the summary. I talked about simulation and this kind of higher order designs and high fidelity generation of entangled state on a Rydberg atom quantum simulator. Talk quite a bit about merging computing with clocks and metrology, which I find very fascinating. So a topic where I'm still learning a lot of new things. And then I talked about some sort of ultimate scalability. So let me come back to this slide. So I said we want very low error rates and we want very large system sizes. And we have this approach, and this approach turns out to be quite fruitful. So we have these 2 qubit entangling gates now. We can get to very competitive numbers, you know, that are competitive with, for example, superconducting circuits, even the best ones now. And I think we can push this quite a bit. This is relatively straightforward. And we can scale these things to over 500,000 qubits. So that's quite unique, actually. And you have all this circuit reconfigurability. And in addition, I think there's very unique opportunities in the context of quantum metrology. So this is sort of the wrap-up slide. With this, I want to thank all the like funding agencies and all the people who work on this, theory collaborators, students, and so forth, some of which in the audience. And with this, I'd like to thank you for your attention.
So the multi-ensemble clocks with the sort of diameter is improvement. How do you think about the? I guess you have to divide up your atom resources into different bins with different. You know, you're doing classical or these contained gates, right?
Yeah, right.
And so you're losing. You're not using all of your resources at the most sensitive state. So is that just like an order 1 factor? Or?
That's an order 1 factor, it turns out. Actually, you need like 10, 20 atoms because you don't need to do full phase estimation with the slow one, because you just need to do some estimation like up to like factors of 5.
Okay, the next.
And then you have to just get your phase width error low enough, and then you can estimate it. They already did it in the first paper. So you need, like, if you do quadrature, you need about 10 atoms or 20 atoms. That's kind of what I want. And you gain quite a bit. If you had a low atoms, you could do this, it would be improved dramatically. Because you could just go to very, very long lengths until you hit the atomic frequency. Yeah.
You showed for the large transports of dynamic coupling. What exactly was that?
I forgot. It's a nil. Oh no, it's gone. It's a K. It's a K. It's actually, we're not doing the same sequence anymore, so I don't want to talk too much about it. So we actually switched the sequence. It's a K. Okay, so like to get to very long coherence times, you have to do some dynamic decoupling in the end. It's like you decouple from magnetic field noise and decoupling from like motional noise in the tweezer. So you have some differential light shift and the atoms move around, and you have to decouple from like phase noise that comes from motion, basically. And then here's a little bit more because you move them around. Also, the tweezer depth changes a little bit, for example, so you have to decouple from that stuff. So like you need to do something. And a specific sequence is a nil. Oh, I forgot. There's so many sequences. I can never remember their names. It's a nil dB. No, this has to do with the acousto-optical deflector. So we use a new type of acoustic-optical deflector. That's right. That has its own challenges. It's not completely done, that story. Once you go to we're trying to explore some sort of the technical limits of scaling that thing. And you can transport that far, but there's some tricks involved that we had to kind of figure out. We're still figuring out. Let me put it. Yeah. Okay.
Okay, one more question?
That was one more. All right.
Not maybe, I'll just ask one.
Okay.
The question of that. So you talked about, yeah, I guess I just wanted to understand these, PhD states. Two things. One, like you sort of sketch the circuit schematically, but
Yeah.
like physically, are you just moving things in 1D or is this something?
This is
sophisticated in order to build up?
Yeah, this is.
Circuits you need for that?
So currently we just do it in 1D. I'm not sure if I have this. Yeah, so this is some sort of. And it doesn't even, most of the circuit doesn't even use single qubit control. It's just like you really literally just global control plus gates.
So yeah, and then I guess my other question was, with these parity fringes, do you look differentiate between to take out any common mode phase noise, or is it really just the contrast losses that
We don't. So this is all global. So there's no. Yeah. This atom. It's atom.
look differentially between two?
Yeah, they would be better. We didn't. Yeah, we didn't do that, and we should have done this. Maybe, or sure we should do it now. That's right. You would see higher contrast. That's right. That's right. We didn't do that. Like, the reason is we don't have so many atoms in this 1D version, because you need a parity signal that's reliable in one shot. So you need multiple copies. Like you need a certain number or more of copies to actually do this right.
Right.
Yeah, that's right. So this atom laser coherence that you see here,
Okay.
but it's not the atom laser coherence in a long Ramsey in the end. So the limiting, so there's two things maybe, like the one is the fidelity of building the state, and the other one is like the coherence loss in the actual Ramsey interferometer. So we're currently limited by building the state actually. So this has to do with certain idle time because you move around here. That's not a principal problem. It's just a question of how good your clock laser is, because you lose clock laser coherence in here. Our clock laser is just like experts 5 10 to the minus 15, but you need, if you had 1 10 to the minus 16 or something like this, like you could actually, this would be no loss at all. So you would just have the 2 qubit gate. And even with the current 2 qubit fidelities, you can estimate the 50 to 100 TGs that you can make with above 50%.
Great. Okay, well, I think Manuel is around the rest of the day if there are more questions, but we'll wrap up this. Thank you again.
Thank you. Did I just, okay, I'm just gonna leave.